overcoming some of the limitations of AFM, as well as trying to see that can it have a much broader application than AFM. So what does the probe does? It do the profiling of a surface as well as it also do the imaging of the surface. So some of these work is in the process of, patent has been filed, some discussions going on with some industry. You can see some of these industry we are working with. We went to this Imami paper mill, Force Marshall visited us. We sent our product to Blue Chip Electronics in Hyderabad. So some balls are rolling, but not really that great that I can say that it's in the production stage. But possibly it will take some time. It will take some time. Okay, so this takes me to the outline of a talk where I will be giving some brief introduction quickly. Then since it is about sensing to single photon, I will be telling you different forefront of research where optics has been utilized, or largely for many of us, and especially in this part of the country, where people think optics about lens and glasses. I think that has gone much beyond that, and therefore, I will be talking about some of the latest what people have been using in optics for sensing application, and therefore, of course, there are imaging as well as very hot area is photonic integrated circuit, something like what you have as a large scale integration in electronics. So I will be talking about some optical sensing systems and how does they work. Some in-house build system which has been utilized for some system development. Give you some brief about the single photon, what a single photon, how it can be used, how it can be generated, and then how it can be interfaced for different application. And maybe slightly higher up stuff towards the end, that how can you have polarized single photon. So slightly maybe we can neglect that part if time does not permit, and then some conclusions and challenges. So if you quickly see, if any optical sensing systems you require these three things. What you require some light source. So in our lab we work with light source, but the light source what we use is not the laser. So in laser you have a Gaussian wavefront, right? Gaussian, the beam profile is Gaussian. But then we try to create a beam profile which is more, which you can say that we try to structure the beam profile, and those are called as structured light, or you can also say as orbiter angular momentum beam. So I will show you in one of a slide about that. So we work with light source, and then we of course develop the sensing probe in our lab. And also you require that. So these two things we are working with. Detector we largely purchase, and then of course signal processing unit sometime we use, sometime we develop, sometime whatever is available commercially we try to tamper it to customize as per our requirement. And why there has been a lot of talk about this optical sensors market, there is some brief number distribution because things goes by economics, and the graph looks quite quite encouraging, that over a period of time it is expected that these market will going to increase further, and therefore the motivation also largely comes from these statistics which ask you to put your effort in the direction of these areas where things has a potential to be commercial as far as application is concerned. Okay, so where all systems works, it works in everywhere. So if you consider optical sensing systems, the best is your mobile phone, that what you are using on. So you know that nowadays mobile is no longer mobile, it's everything. It's everything means it's everything. And one of our most important uses that has recently been shown in one of the latest strike by Gen Z is using it as a camera. So everything and anything is captured there, which is basically some sort of a small device integrated with the mobile phone, where you can take image, you can make videos, and then of course there are further things which get into that. Then you have in manufacturing, I will be talking some about them. In infrastructures for structural health monitoring, people have been using. Healthcare, I will talk about. This is a very new area, and I think in India there are only maybe our group and one more group who are working in these areas. But there are full-fledged industry in China and also in US who are working with what is called as a photonic wearables, like the electronic watch that what we use for monitoring the health parameter of a body, which really start picking up after Corona, post-Corona. Now it is, people are looking at that down the lane, it will be a customized healthcare. So you sit at your home, you just take some patches, and then you do all the, whatever you want to do, you just do. Like nowadays you have this, to measure the sugar, you have some strip available in the market. So think that such type of a strip can, is it possible to measure the bilirubin count, or is it possible to measure the liver function of your blood sitting at home? So that's the bigger picture. So in that direction, a lot of work is going on, and I will be discussing, maybe I will give you some glimpse about that. Environmental, transportation, these are a lot of work are there, but possibly time may not permit to go that, but I will try to cover some of them as we progress ahead with the slide. So largely, if you consider light as a some sort of electromagnetic wave which will be utilized for monitoring any of these parameters. So you have to work with one of these light property which are dominant, like phase, the amplitude, phase, wavelength, intensity, and polarization. So you play with one of those parameters. Either you tailor them as per your requirement, or it will get tailored depending upon the surroundings. Then accordingly, there are these 4 principles. So you have to use one of those principles to make a device. And depending upon what you want to monitor, therefore it becomes very, very important to choose one of these principles. So these are some principles, and of course applications are in all physical, chemical, or biological systems, and key features are here. I mean, which largely electronics many a times will not provide you key features like multiplexing. You can't have a multiplexing with electronics, right? You can't multiplex. You can do some amplification, amplifier can be utilized to amplify, but multiplexing, people are trying to use IoT for that purpose, but then again, it has certain limitations. These is expected to be compact over a period of time, for especially for students. Now these photonic integrated circuits, what are coming, those who have seen the laser source in the lab, so you can think that those will come printed on some small chip. You have all the laser component printed on a small chip. Now you can imagine that will be the size of a laser down the lane. I hope you can visualize. Some small chip will be there, and it will have everything there. The active medium, the pump, the oscillator, everything, whatever you think will be on a small chip, and that is as good as a laser that what you use, big laser that you see in the lab. So that is where currently optics is trying to be pushed to. Okay, so this is one case where laser-based sensing, people have been using laser, and all of you must have used this. Ellipsometry is basically one of our important I should say instrument for characterizing the material, and there, depending upon the type of the systems that you use, you can have a resolution down to a few picometers. LIDAR, for those of you who understand atmospheric science, this is making a lot of impact, where light detection and ranging, similar to what sonar people used to talk at some point of time, where sound wave was utilized. Now people are talking about LIDAR, especially for mapping the vegetations from some distance. So LIDAR integrated with drone will going to be the future technology. So you integrate LIDAR with drone, and that is what future will look like. This is laser Doppler vibrometry. This is again based on the very beautiful concept of Doppler shifting, and it allows you to monitor the non-intrusive measurement of different type of fluid can be done using this laser Doppler vibrometry. So everywhere this is laser playing an important role. Then of course quantum sensing, something very hot area. You know that the government of India has initiated National Quantum Mission Program, where quantum sensing is one of a vertical along with metrology, and people are using different type of lasers to achieve sensing at quantum levels. So these are all laser based. Then you have another area which is They also use laser, but the working principle is different. That is what is called as a plasmonics-based sensing. So I was talking about that. So there, what happens is you take some metal dielectric interface. So you have to choose right metal. Largely, these are noble metals, and you have to excite those metals with right type of light. So those light has to be TM polarized. So I was talking with Mr. Mohanty. He was coming with me in the morning, and we had a lot of discussions related to this. So, if you choose right polarization of a light and you take a metal dielectric interface, metal being the gold, whatever you are wearing in your around the neck or on your finger, if you choose that gold, air being a dielectric, and if you incident a right kind of polarized light, then you will excite some coherent oscillations of electron at the interface of metal and dielectric. That is at the interface of gold and air. Now these, since you can tailor the properties of the dielectric, you know that dielectric is a function of a wavelength, or therefore refractive index is a function of a wavelength. So any change or any perturbation that will happen in the dielectric medium, you can going to monitor them, and this is exactly what is being shown here. Extending that, people are using what is called as a surface enhanced Raman scattering, which is SERS technology, where the field enhancement can be increased many-fold, order of 10 to the power 7, 8, 9, 10 till 10 to the power 13, 14, by suitably choosing some nanoparticle. So that's another advanced area of plasmonics where people are using it, and now there are some commercial available systems for cancer detection using SERS-based technology. These are company spin-off from the place where I did my postdoc. If you just Google, you'll realize that it's already now in the market for this based on the plasmonics. Okay, then this is what I was talking to you about, the structured light. Now you see, this is a type of a light where there is no light in the center and all around you have the light. So generating this light requires some special type of, I should say, it requires some special type of setup where you try to play with the phase of the light. And if you do the optics correct, you will able to generate these different, phase profile where this L is a topological factor and phi is the azimuthal coordinate. Let's not go into those details. But you can have some phase similarity in the beam, and that can be utilized for a lot of application. People are expecting that this may also be utilized for future communication. Again, when I say future communication, it may not be for long distance communication, but for short distance communication. This is what I was trying to tell you, that one of the application is you can, so like what we have read in our class, the 12th high school or college, is about creating these interference fringe using some light source like laser source, right? So one can also do all those optics using such a structured beam, which give you certain advantage over the conventional stuff. Now those advantage, how to explore that is of course a matter of a research. So again, similar type of beam has been also used to develop some Dopplers, some Doppler effect has been studied with similar type of beam for different applications. Then comes this hot area of research, which is called as a quantum sensing, where you try to use different type of advanced material, and one of our most widely used studied material nowadays is diamond defects in diamond. So basically what we, when we try to purchase diamond for ornamental purpose, then you don't want defect there. So if you say that diamond with a defect, possibly diamond without defect will be costliest. This is what I believe. But for a physics, a defect in diamond is more lucrative than a pure diamond. And therefore, a lot of people does research where different type of centers are there inside the diamond. I should say different type of vacancies are there inside diamond. It can be silicon vacancy, it can be nitrogen vacancy, it can be chromium vacancy. And then these vacancies, utilizing its spin property, people have developed a very stable thermometer which can measure temperature of order of 13 10 to the power minus 14. That order of magnitude has been already established using such type of NV centers, where people are thinking that future device of MRI will be replaced by NV centers based MRI. This is what the bigger picture is. Then can we have a quantum communication with existing fiber network? And this is a big question that is being, there is no clear cut answer to this question at this point of time. But it is visualized. There's a group by Professor Prem Kumar in Northwestern University. He's a big guy working in this area. So there's a strong feeling that with certain modifications, the existing fiber network can be utilized for a quantum communication application. Then people also used a squeeze-like concept. This is another beautiful concept in physics which people use for communication as well as for sensing application. So what I'm trying to just briefly tell you that what are the different techniques or what are the different I should say systems which people have used, starting from either laser or tailoring the profile of a beam, tailoring the phase profile of a beam to make a structured light, or plasmonics or quantum for different applications in the area of sensing. So let me go quickly to other part, which is where people have been using conventional fiber to make interferometer, different type of interferometer. And then once you make an interferometer, you are aware about all these names like Michelson, Fabrica, or Sagnac. Sagnac possibly you may not have read, but it is, you see, all these are working interference, but the concept of working is different. Some are trying to monitor the phase, some are trying to monitor the intensity, some are trying to monitor the polarization, and this is what makes it different, that what is the application will decide which one will going to be utilized. So we have used some of these in our lab, and this is what one diagram you can see here, that we are making some small cavity. So this is your reflecting surface, and this is your some external field. So you basically perturb the cavity with the external field. This get governed by basic equation. So the value of the D and whatever the index in between get modulated, and therefore the phase factor will get modulated. The thinness of the cavity will get modulated, and therefore the FSR will get modulated. So what you can see that for different value of D, you can see that the FSR is changing, right? So again, if you want to make a very sensitive device, you want to have a FSR which is, the distance between the two fields should be low. Then you can develop such type of interferometer. So the beauty is that you can customize the device as per the requirement. And this is all these devices are, this is what has been written, that these are reconfigurable. You can configure them and reconfigure them depending upon what type of performance you expect from the device, and they can be multiplexed, and it can be integrated with different type of other devices for many other applications. Then you can also make hybrid cavity. So hybrid cavity is like it's not only the air cavity, but also the material cavity will come into play. So here the material cavity largely comes from this collapse region, which is also act as a small cavity, and then you try to interfere the fundamental core mode or higher order core modes with one of these cladding modes. So these are fundamental core mode, these are higher order core modes with one of this cladding mode, and then you get interference pattern, something like this. And if you make a cavity, you see that you are able to discretize the interference pattern. That means you are tailoring the FSR, and therefore you can do the very precise monitoring can be done. There is a concept of what is called as a Vernier effect. What we see in undergraduate lab, we have a Vernier caliper, main scale and the Vernier scale. So you basically try to use the vernier to ensure the magnification part of the measurement. So if you are unable to see some small measurement, you apply the Vernier concept and you are able to detect them. But that you require two type of scale for that, right? The main scale and the Vernier scale. Similarly, here what we do is we make two interference pattern. One is a reference interference pattern, and interferometer, or another is a sensing interferometer. And then we detune the cavity very slightly. Now, how slightly it need to be detuned? One has to, do the calculation and see that you are on the right part. So if you can now superpose both of them, you get some combined spectrum. Now, rather than individually tracking these peak in real time, we track the combined spectrum in real time, and this allows you to do some very fine measurement. And this is a concept which we utilized for the development of optical profilometer, the counterpart what we are saying for the AFM. I will be discussing about this as I go ahead with the slide. Some of the developed device in the lab is for magnetometry. What we see here is the cavity that what I was talking about. So the material that will act like a cavity, I mean the material that will be from where the light will be reflected, so that you have some cavity. Please recall D and N was responsible for modulating the phase and therefore the FSR. Therefore, we intentionally choose some membrane, which was a PDMS membrane, and on this PDMS membrane, we coated this zinc-coated neodymium magnet. So this was coated on this flexible membrane, and then we, exposed this to magnetic field. Now, exposing this to static magnetic field was not something which was very excited to work on, because there was some report about static magnetic field. People have reported to use it for interferometry. So what you can see that these were characterization, these 20 micron, 30 micron, 40, these are all D distance. So you see that by varying the D distance, you are monitoring the FSR. Important part that pop up here is the direction of the field can also, not only the magnitude of the field, therefore acting as a magnetometer, the direction of the field was also what you can make out from this system. So if the field is repulsive or attractive, can be determined by the slope of this, and depending upon for a given value of D, and the condition, phase condition, what it will going to fulfill, you can tune the performance of the device. So these are basically vector magnetometers. So you can also monitor the direction of the field. Interesting was not the static field, but the dynamic field. That means if you give V equal to V0 cos omega t, so if I can determine omega, I know t, I can determine the time varying magnetic field. And this is what makes the works more interesting. So then we applied some time varying magnetic field to this diaphragm. You see that we have taken the time response of that around 615 hertz. And what was that? Did I? Oh, fine. So this is what corresponding to 615 hertz. So if you do for different time series data, if you take for all different hertz like 200, 400, 615, you see these are all these some noises. What you can see here, but these noises are much small. The signal to noise ratio is very high. So for different value of omega, you can calculate the value of p. So determining not only the static field along with its direction, but also the time dependent magnetic field was what the USP of this work was. So then we try to calibrate for different different frequency. How does the device look like? And you can see that this largely remain constant. They were showing that the device can be utilized over a broad frequency range. I was talking about mapping some underwater. So this is these are the two view graph. This is a gold standard in the market. So if you purchase a hydro from a market, and if you try to monitor the frequency response of those hydrophone, what you are going to realize. So what you are seeing in this particular graph, this is a sound of a dolphin. If you take the sound of a dolphin and do the signal conditioning of that in MATLAB, these are also available on internet. You can find it on internet. So these are frequency response from a dolphin. And if you have to track a dolphin inside water, so you require such type of hydrophone. So if dolphin will make sound, some hydrophone should be there to catch that sound. So by placing the hydrophone suitably inside water, you can locate the XYZ coordinate of a dolphin inside water. This is what we are trying to show here. So this is a BNK hydrophone. So the cost of a hydrophone, this hydrophone is typically around 60,000, but the signal conditioning unit cost around 13 lakh. So the device is 60,000, but 20 times the device cost is the signal conditioning unit, where a lot of signal processing has been done to ensure a clean signal. So this is market. This is what we have developed. It is just raw data that has been plotted, no signal conditioning. So it is only the device. And therefore you can see that there are some peaks that is popping up. So those are the noise. Those are the noise. So what we are trying to tell you here is as follows. So if you can, these are the images of the two systems. This is what market give you BNK, and this is what our systems look like. So this device can work quite close to around 4 kilohertz. Of course, now we have further extended this result to around 17 kilohertz because in optical domain, determining the frequency beyond 35 kilohertz is still very, very difficult. It's very difficult. So since you can get an interrogator of 35 kilohertz, so F by 2, that means 17.5 kilohertz is what we can do. These numbers, what is saying, what we are showing you is state-of-art numbers, and therefore this led to the patent of this device, which we are in the process of discussing for its commercialization with some of the vendors. Okay, this is what I was talking to you about optical profilometry based on the concept of vernier interferometry. Please, those who have done AFM can recall this image. This is some sort of a specimen that is given to by the industry to calibrate the AFM. So what it says that it tells you it has different type of structures over which probe moves, those stylus moves, and it gives you the profile. What we have done is this dotted line, what you are seeing here, this dotted line has been profiled by AFM and also by our device. And what you are seeing here is a RA value, which is a standard value, accepted by the whole community working in the area of condensed matter, is 55.88 nanometer, and this is 55.55 nanometer. Now, somebody may argue that the AFM is better or this is better. Our argument here is which one is better is please note this AFM, the unit that comes with signal conditioning. Here we have not done any signal conditioning, and therefore these are again raw data, and therefore we can always make it clean data. But the intention is not to show you the clean data, but intention is to show you how robust is the device, that it's picking those systems, quite, I should say, quite smoothly. Important thing is AFM cannot do the measurement for all values. So with AFM, if you want to monitor AFM with AFM systems, if you want to monitor, let's say 1 micron, or let's say less than a micron. Possibly nobody will like to use AFM for that. Only if you go for something like order of nanometer or few tenths of nanometer, then you go for AFM. Our device has an operating range starting from 5 nanometer to 1 millimeter. That means you take a device, 2 probes will be there. One probe will work for anything less than 1 millimeter, and another probe will work for anything less than 100 nanometer. So either of the probe, you just insert the probe in the system and system will work. So this is what I have shown here. It is from nanometer to millimeter. This is just to show you how stable is the device. You increase in the 100 micron steps, you decrease the 100 micron steps, and you see the repeatability of the device. This is one video. This is what Imami Paper Mill was interested to measure the paper roughness of a paper. So this is what how we make our samples. So this is one paper that was given by the company, and we just try to prepare the sample preparation. It's very easy. It is not those who have done work with AFM will realize that handling a stylus is very challenging. It's very difficult. It's break at a time, and generally students are not allowed to touch that. But here it is not the case. A student can easily use the device. It's quite robust.
So you just have to put on the glass slide, and then this is where the device is lying. This is where the interferometer based on the Gornier concept is lying, and you can see, if you carefully see, you'll see that this has been placed on XYZ movement scale. The working range for this is around 150 millimeter. So, and then in real time you can take the data. So this data is changing, and there's some MATLAB code which will go in the background. And if you carefully see, you will see that this is moving. This one is moving. So basically, it is scanning. It is the same raster scanning that is done in the AFM, what we are doing here. So after some MATLAB program, it will going to give you something like that, where thickness of the paper is this much, roughness is this much. One can monitor that. We further extended to see that how does the image look like, and this is the image profile of, this is one of, again, industrial sample. We try to image them, and this is how the image profile look like. This is how the image profile look like. This is what I was talking to you about. The another part, the photonic variables. So our device, our main aim is to, currently we are trying to work something on physiological monitoring, but there are some projects where we are trying to handle these two, smart clothing and human machine interface, and of course for biomedical device, but these will take time. So how our system works, it works on one of these. So either if there is any twisting, rubbing, bending, pressing, or stretching in the body, it will going to pick that, and it will going to tell you about the health condition. Advantages, of course, are these, and the most important advantage is what makes it different than the electronic counterpart is biocompatibility and multifunctionality. So I'm sure many of us in our room must be having minimum 3 to 4 mobile phone lying in one corner. And if you are a smartwatch guy or girl, then you'll realize that 2 or 3 smartwatches lying idle in some corner. Down the lane, where will they go? Maybe after 10 years? The amount of electronic garbage what is expected to be generated is enormous. So can this be overcome? And this is where photonics will possibly play a role. These are all underwater compatible, what the electronics counterpart does. And best part is you can't wear your electronic watch around the neck, right? If I have to monitor the bending of a neck, or if I have to monitor that how much a patient or how much a person who is going through a rehabilitation process can move his or her knee, you can't put that watch there, right? Watch can give you few parameters of a human body, not all the parameters. But this is what we are saying, that we have customized the device for different applications. This is just glimpse to people, especially for student to get excited about these work. So this is some real-time pulse monitoring that is going on a subject. This is the pulse monitor. It has been kept here. And these data, this particular data, if you see carefully, before A, you see B. So what you go into the market, what is available is PPG. You take the systolic and the diastolic peak, or you go with the piezoelectric. These are the two systems that are available in markets. PPG is still not that great, but piezo is what people commercially, whenever you go for pulse monitoring, it shows you the peak and the dip. Our system, if you see, there are 2-3 more peaks it is showing. This work is also in some sort of a collaboration with AIIMS Bhubaneswar, and the doctors are very much curious about these peaks. And then when you slightly dig into the literature, there are some reports around 1955-56. Of course, by electronic system, where they expected that there should be these tidal wave or dichroic peak, or this what is called as a dichroic notch. This is what is called as a notch, where it is expected that it gives you more information about the health condition of a human. And therefore, initially, somebody who are into this business came and they were thinking that these are noise. Then we did it over these many cycles. You can see that it is over multiple 500, 1000 cycles, and every time the report was same. And then we try to compare the heart rate with the different commercial available meters, and then you can see such type of correspondence with the existing systems. So this, what I try to show you is, you put it on the hand, you can use it. You put it on the people who use pan masala and gutka, after some point of time, they may not be able to open the mouth because of some problem with the mouth. So in real time, you want to monitor that subject over a period of time. that how much they are able to open the mouth. You can't, you have to put some device. So this is what I said, that these device can be customized for different part of the body. And therefore, this is what make it more interesting than the whatever the commercially available devices are. These have signal to noise ratio better than the electronic counterpart without signal conditioning. And we are now trying to see that how this data can be taken on the mobile phone. This was more of a, I should say, this was more of an applied part of our work. What we're going to get into more fundamental part, what we do related to that, and this is plasmon-mediated coupling of polarized single photon. So for students, especially single photon, you know that how communication in the current systems works. It works in bit in form of 0 and 1, but what we are talking about is some superposition, like 0 and 1, and therefore these are called as qubit. And this is what people are expecting will the future quantum communication will be, using these qubit system. Just to give you a feel, if you take a laser, helium neon laser, that what is available in your lab, you must have seen that helium neon laser, that is typically of 1 milliwatt. So you take that 1 milliwatt laser, do some simple calculation, and that 1 milliwatt laser operating around 635 nanometer will give you 10 raised to the power 15 photons. You see, this is the number. That means the 1 milliwatt laser in your lab is generating 10 raised to the power 15 photon. The idea is to make from that to 1 photon. Now, it is, therefore we should know how to create this one single photon. Many of us will have a very intuitive feeling that we go on reducing this 1 milliwatt to a very small number till it becomes one single photon, right? 10 raised to the power 15. So you go on reducing 1 milliwatt to, microwatt, nanowatt, picowatt. So this is what people also does, and they are called, this is called as attenuated laser-based systems. But then these has a lot of challenges, lot of issues. People have, some of them have demonstrated, but not really functional to an extent that you can use it for different application. What people have been using and what is commercially big success is a single photon or entangled photon generation based on the concept of SPDC. SPDC is spontaneous parametric down conversion. It's a nonlinear process where a laser light pump a nonlinear crystal. Now these crystals can be different type depending upon what type of entangled photon you are trying to generate, and you can generate 2 photons which are entangled. Now this is what people have been using, and you must have heard in 2023 that China demonstrated quantum communication between China and Austria, which was a big success. So the basic generation of single photon that happens, or entangled photon that happens, was using this process. India have also demonstrated this. SPDC has been demonstrated by ISRO. Some guy from SAC also was part of that. So this process of single entangled photon has been generated. Of course, whether Professor Ajit can tell more on that, if what is the state of art. But earlier it was, I think, it was order of kilometer or beyond. If it has gone, I am not very sure about it. I'm talking about satellite communication. So these are entangled photon. That means entangled means it's something like Jurma. So both are, one property of one will going to affect the property of other. This is what you can visualize. So this is what is entanglement is. What we are talking about is a single photon, where you can think it as some sort of a quantum emitter. So it is a 2-level energy systems. So if you incident light with particular frequency, then you expect that the electron will go to excited state, and as it comes down, you have to ensure that these energy level are clean so that it should not give you multiple photons, unwanted multiple photons. So you can generate single photon out of that. I hope I am fine with time. 10 minutes? Okay, fine. So this is what we use in our lab. We use the concept of generating single photon through quantum emitters, and we use different type of quantum emitters for this. We use different. So then, what are the properties of the single photon? If you see carefully,
Uh, all these thermal light source LED panels that you are using, these follow certain type of statistics. So what it follows is a super Poissonian statistics. What are these? If you see this plot, so you are seeing G square of tau. This is called as a correlation. So what it correlates? It correlates the intensity at 2 time. So T and T plus tau. So this is called as a second order correlation function. It's a square of electric field. Therefore, you are talking about correlation, second order correlation. So if the second order correlation is less than 0, you see this is 1. Sorry, less than 1, not less than 0. If it is
less than 1, so you see the red curve, which is called as a sub-Poissonian. So if second order correlation is less than 1, that means if the photon are anti-bunched, it is not bunched photon, not together. They are separated out well. So if these are anti-bunched, it will follow the sub-Poissonian statistics. Then your second order correlation will be less than 1. Till date, there is no. So, okay. So what is ideal single photon? Ideal single photon should have second order correlation equal to 0. But ideal is always ideal. Till date, there is no reported literature where second order correlation is close to 0. So in principle, you should able to get a second order correlation close to 0. But then, of course, there are limitations. Till date, it has not been done. So when we talk about internet, we say that it is kbps, mbps. So the current state of art with single photon or entangled photon is 10 raised to power 5. So it is 10 mbps. The count rate that what one can generate for the communication is close to 10 raised to power 5. So it is expected that this will going to get increased over a period of time. So ideal single photon, these are the properties of single photon, that it should have these sub-Poissonian statistics, it should follow that, and it should be anti-bunched where the second order correlation should be less than 1 and ideally close to 0. So you do this experiment in the lab, do the calculation, and then see that whether you are getting it close to 0 or not. If you see a bigger picture, what people are trying to aim is to have a quantum internet like what the classical internet is currently you have. So even for the classical internet, what you require some sort of a signal, and you require some sort of a medium which can carry this signal. Similarly here, you require some sort of a quantum interface or channel, and you require some quantum emitter or node. So what quantum emitter we are talking about is basically the node, that what you see in the classical internet also. Once you have generated this single photon, you know that okay, second order correlation is less than 1, it is close to 0. How to detect them? So you detect using some sort of a experiment. Now this is HBT interferometer. This is a quantum interferometer where you put a photon on a beam splitter, and then you have a 2 detector, and then you correlate them in time. Now it's look a easy setup, but quite difficult to do it in the lab. So then you use this interferometer to detect this single photon. And then it can be further put in different interferometric pattern. And then if you put in different interferometric pattern, depending upon what you are interested to identify as, let's say, for quantum sensing application, you can use them. So I was talking about the quantum interface. One of a quantum interface or quantum channel, what people use is optical nanofiber. What is optical nanofiber? You take the conventional fiber, and this is, if you see, this is around 125. So it is close to 250 micron. Whole of this dia, you see the cursor, this dia will be close to 250 micron. But this 250 micron has to be brought around 200 nanometer. I hope you can imagine. So what has been shown here in this particular image, this is a human hair. Human hair thickness varies around 20 micron to 60 micron, typically. So if you wrap an optical nanofiber or nanowire around a human hair, it will look something like this. So this is illuminated with a helium neon laser. So this is human hair, and you are wrapping it around. This is 200 nanometer optical nanowire. So this is a definition which is in the literature, that your operating wavelength should be less than the diameter of a fiber. Then you are in a optical nanofiber domain. And the advantage that comes, you see the type of a field. This is same concept of what you have in tunneling in quantum mechanics. It's the same concept what you get a evanescent field in case of a light. It's the same concept. So you get exposed to quite an amount of field, and it is this field which helps you to do a lot of sensing application. So people place atoms, which will be quantum emitters in our case. You put quantum emitters there, and then you try to generate the single photon and interface this single photon through these optical nanofiber at different end. And therefore it acts as a quantum channel. The bigger picture is, can it be integrated with the existing fiber network or not? That's a bigger picture. In lab, how it is done, this is a video which you can see. This video is self-explanatory, but what you can see is you have two stages, and you have an optical fiber placed there. If you launch the fundamental mode, it will go nicely. This shows the fundamental mode. It moves. You have to make suitable flame. The optimized images of flame has been shown here. These are camera taken image. So you have to optimize the flame, and then you have to heat this optical fiber, pull it through this computerized stage in either direction. If you heat more or pull less, it will break. If you pull more or heat less, again, it will break. So you have to be very careful. And if you make, then you see a lot of field will be in this area. So this is what we have developed. This is 330 nanometer that has been developed in our lab. And then you use it. It is scalable. These are some of the property. All these are using at room temperature. And then you can make different shapes out of it for different applications depending upon what you are interested in. So this is how optical nanowire can be developed. So interface, we talked about interface. Now let's talk about, so quantum internet require quantum interface and quantum node. So quantum emitters are basically quantum node. So one of those quantum nodes, these can all act as a quantum emitters or quantum node, like quantum dot NV centers. Advanced 2D material like HBN and CNT, some of these have also been demonstrated in literature. Those who are interested can look into the literature. The problem is that except NV centers, with many of these are some of the limitations. The single photon spectra, what it generates is quite broad. If you want to create a polarized single photon, you are gone. The polarization of this single photon amounts to around, let's say, the very best reported through these techniques is close to around 20%. Polarization is 20%. A concept of blinking effect is something like blink it, what you get in the market nowadays, blink it fast, you get things fast. It is something like blinking of eye. Similarly, you have a blinking that whatever the quantum emitters you have, if you incident a laser light on it, it will give you a photon. But then this photon will disappear. So there is a lag between the emission and the generation. So it's blink. So this blinking do exist with many type of this core shell quantum dot. And therefore, this is a big challenge. Therefore, you cannot continuously generate the single photon. If you require 10⁶ mega Mbps type of generation of single photon, it's very, very difficult. And therefore, you have to overcome this blinking effect. And of course, it has a high decay time, and therefore, getting those single photon very fast will going to be a big challenge. Okay, so can this be addressed? Yes, it can be addressed. It can be addressed by integrating plasmonics concept to these quantum emitters. I will show you. So I have discussed about what is called as a propagating surface plasmon. I discussed that you take a metal dielectric interface, you excite suitably, coherent oscillations of electron happens at metal dielectric interface, and this propagate. And as it propagates, these are called as propagating plasmon, and this is how the field will look like in propagating plasmons. Then there are what is called as a localized plasmon, that you localize the electron around a nanoparticle. So to create localized plasmon, you can make any, you will see that all these are reported in literature. All these different shapes are reported in literature. You can make all type of nanosphere, nanocell, nanorod, cluster, cage, nanostar. So all these are made from a gold. So this is what you can have a, some metal nanosphere, you apply field, the electron cloud will get displaced and they will going to now oscillate around that. And therefore it creates a localized plasmon. Similarly, you can take a nanorod, again, you can have a localized plasmon. So you can take one of these. If you plot the localized field versus these, thin metal field, you see that field are largely confined at the interface here, that is a surface in propagating plasmon. In localized plasmon, you see the concentration of the field around. You see the concentration. These are called as wherever the field is more, these are called as a hotspot. And these hotspot, if you can place a quantum emitter in these hotspot, you're going to get a polarized photon. That's the basic concept. Because it is these field which will going to trigger the photon to come down in a specialized fashion, because these are also polarization dependent phenomena. Okay, so to have a very strong light matter interaction, you use these metal nanowires. And this is what I would like to show you here is that we took 2 gold nanorods, put a quantum emitter in between.
And then you see that what you get is a polarized single photon. These are some salient features, need not to worry much about these. These are some of the aspect. What is the take-home message here? The take-home message is to generate a polarized single photon, you have to have plasmonic has to be brought to create a polarized single photon, because then you can really decide upon the direction of the electric field that is there. And that will help you to generate a polarized single photon as high as 99%. And this has also been, we then try to do these, calculate these for different aspect ratio of the gold nanorod, showed some hotspot in the field, calculated some local field enhancement, and then there was some experimental paper
which people reported, and then we try to correlate the experimental result with whatever we predicted, and that seems that you will see that it's turning out to be a perfect as per our calculation. So to get a polarized single photon, you need to have plasmon. Now, what I showed you is something what I showed you is optical nanowire. So this is a big system. So it can be utilized for long distance communication. But what if I need to do something on chip? To do something on chip at a lower level, how to do that? So for that, you have to make some sort of apodized cavity. This is what you can think of. Photonic crystal is a classical example of a one-dimensional cavity. So you can apodize the cavity. And this is something it look like that you tailor the period around both sides. This is what apodization is. And if you put a gold nanorod and attach quantum emitters to it, then what you expect that this apodization will going to give you all these whatever is required to generate single photon in on-chip device. So these are basically for on-chip device. The other what I discussed, polarized single photon, is for long distance communication, not for on-chip device. This ensures that one of a major challenge of all these on-chip devices is a large scattering loss. So one has to develop a system like that the scattering loss in per round trip should be minimized. And this is what this apodized cavity will going to give you, apart from the stronger field confinement, and that too with a very less grating period. You can see that these are sensitive to modes, polarization dependent phenomena, and therefore again you can get the polarized concept into consideration. I think with this I will stop. These are some of the conclusions and challenges. We tried to talk about the different optical systems and some latest development using different type of stuff in sensing. Then some we also try to demonstrate, we try to discuss about some developed device using these micro nanostructure platform and integrating to advanced material to develop magnetometer, hydrophone, profilometer for applications. Then I try to touch upon what a single photon, how it can be generated, how it can be detected, and then how you can interface them suitably for efficient coupling, and how GNRD has an advantage over gold nanorod over gold nanorod dimers, and how these can also be integrated to on-chip single photon design. The challenge largely is that how to take all this from lab to the industry. So that's a big challenge. We are trying to see how it can be done. With this, thank you very much.
Yeah, for an inspiring talk on single photon and its applications. Now it's time for questions. I think there is one hand. Please stand and ask loudly. Or put one front.
Sir, you said that we can use quantum internet, like that is a domain equivalent to the current internet with quantum interfaces. Can you please elaborate on what exactly are going to be the advantages of that form of internet over the current existing technology?
I mean, this is quite well known that current technology has a limitations in terms of data breaching. Every now and then you hear about cyber security and stuff. You must be hearing about that. So it is expected that if you introduce quantum communication, data is more secure, because the very principle of this entanglement will help you to secure the data. It's something like that. Somebody, if you want to touch your data, you can think that it will collapse. Something will change to that. So you can just think like that. So it is very, very secure that way. And therefore, there is a race for quantum computation than quantum communication, because it is expected that whatever the system, that banking system, whatever we are using, those 128-bit encrypted, whatever you see when you operate your bank, can be decoded very fast with quantum computers. So therefore, people are trying to race against time to develop not only different quantum communication protocol, but also for quantum computation. That is more, again, security point of view.
One more. Yeah.
Good afternoon, sir.
Good afternoon.
Sir, as you said, for the variable sensings, that to detect a heart rate or something. Sir, can you?
आ जाइए, आगे आ जाइए, मैं आ जाता हूँ. हाँ, बताइए.
फोटो इलेक्ट्रॉनिक्स तो वेरिएबल्स तो उसको हम लोग एमआरआई और सीटी स्कैन के लिए भी यूज कर सकते हैं.
बिल्कुल. मतलब ऐसे बोल देना कि कर सकते हैं. Somebody has to develop to that level. हम लोगों का एक डिवाइस अभी भुवनेश्वर में भी we went with our device. तो जो ओल्ड लोग होते हैं उनको people who are old, now problem with उनका प्रोस्टेट बढ़ जाता है, तो यूरिनेशन में प्रॉब्लम होता है. तो वो क्या होता है कि आपका एक मसल है जो खुलता या बंद कम होता है. तो उसके लिए इनके पास एक डिवाइस बाहर से जो नायक है, डॉक्टर नायक इज द हेड ऑफ यूरोलॉजी देयर. सो दैट डिवाइस कॉस्ट अराउंड 2.5 करोड़. उसमें लेकिन कुर्सी वर्सी सब लगा हुआ है, थोड़ा सा मतलब इट्स मोर ऑफ अ पैकेजिंग इज वेरी गुड. It's look very good and it has been useful. Now we tested our system with that device. The result is similar. I'm not saying same because for electronic systems I have no optical system, but result was similar. And that we have also written some project on that. So आप ये कहेंगे कि इसको यूज कर सकते हैं कि नहीं कर सकते हैं, लेकिन कैसे यूज करेंगे अभी वो मुझे पता नहीं.
Sir, please.
I have a question. With optical nanofiber was very interesting. You stretch it by heating it tender. So you start with the optical fiber, it's a 2-inch fiber or graded index?
It's a single mode fiber.
Single fiber. But I'm surprised to see that the thickness is in 100 nanometer and you are guiding the wavelength much larger than that. I mean, normally when you solve the...
Yes, you're correct. The reason being we require a lot of field around that. We don't want the complete guidance there. The field which is outside, so it is a hybrid mode which exists So it is air cladded fiber now. Did you get what I'm trying to say?
Here is, I think, also,
Here is-
if I solve mathematical equation for this thing, I have to include the air cladding
Yes,
in that.
yes, yes.
So actual thickness is much larger.
Yes,
including
yes,
that.
yes.
Actually, so it's basically evaluation based.
Yes, it is a evaluation. Same as externally.
One more question again.
Yes.
And the HBT thing which you mentioned about the single photon,
HBT.
HBT,
Right.
handbody point.
Uh-huh.
That was interesting because handbody ground is, from what I know, it works when you have two photon cross correlation or uncorrelated photon. Here you are starting with a single photon, splitting it, but it is split single photon into two, they are correlated. So how do you get a non-zero HBT with a correlated photon?
No, so you take one single photon.
And you split it by beam splitter.
No, we don't know in which arm the photon will go.
No, but nonetheless, I mean, with superposition principle, they are correlated.
They are correlated. So what you are talking about, there are two types of it. What is HOM interferometer? Ongo-Mandel interferometer.
You are doing HBT.
I'm doing HBT. Ongo-Mandel will do whatever you are
So
saying.
HBT requires uncorrelated photon, but I do.
So HBT requires the uncorrelated photon. What you are saying that if you take a photon, you generate single photon.
Yes.
And then using this single photon, you try to put it on a beam splitter, and then you have two APDs,
Right.
and then you time correlate, right? So what is expected from this, that this single photon, let's say they are uncorrelated, the output will be uncorrelated.
Beam split will be allowed.
Yeah.
Any more questions?
Strips that you use on the body to detect issue.
Uh-huh.
So, what exactly do the strips use to check? Like it's based on the skin price. So how do they detect inherent conditions?
So more fundamental principle, what is currently being utilized is interferometry. So we are using a light, we are interfering the light, and then we are tracking the interference peak in real time.
Give us some information about this.
If you take a FFT of an interference, it corresponds to single frequency. So some more intricacies are there. So I just try to keep it very simple. थोड़ा अंदर घुसना पड़ेगा और ठीक है ना?
So I have a related question. If I have sweat, I do the same experiment. What will happen?
That experiment we are doing. So what we have till now, whatever we are able to do is only physiological parameter monitoring. आप biochemical की बात कर रहे हैं. तो अभी हम लोग body में 5, I showed you 5 things. Bending, temperature, pressing, twisting, ये सब अभी हम कर पा रहे हैं. अब अभी जो काम चल रहा है उसमें है sweat, tear, ये सब पे अब काम चल रहा है. तो इन प्रिंसिपल आप जो बता रहे हैं स्वेट से हम बहुत सारा इंफॉर्मेशन निकाल सकते हैं. उसी तरह द होल आइडिया इज, मतलब इसका बड़ा पिक्चर आप कैसे देख रहे हैं? इसका बड़ा पिक्चर देख रहे हैं कि मार्केट में छोटे छोटे ऐसे फंक्शनलाइज सिस्टम आपको दिए जाएंगे. आप जाइए 20-25-30 रुपए का एक खरीदिए, आपको एक सिस्टम दिया जाएगा, जैसे एक सोर्स दिया जाएगा, एक डिटेक्टर दिया जाएगा और बीच में कुछ कपलिंग ऑप्टिक्स दिए जाएंगे. वो सिस्टम को लगाइए, यहाँ पे रखिए, आपका बिलिरुबिन काउंट कितना है वो आपको बताएगा वहाँ. ये बड़ा पिक्चर है. तो आपको डॉक्टर के पास जाना नहीं है बिलिरुबिन काउंट मेजर करने के लिए, लैब आपको नहीं जाना, आपको घर पे आप अपना खुद टेस्ट कर सकते हैं. अगर कुछ फिर सिग्नल मिलता है तो डॉक्टर से जाकर मिलिए. तो वो
Institute of Physics also. So now I request Professor Ananda to kindly deliver his talk, and for this session may I request Professor Dhruvananda Behera sir to kindly chair the session.
Okay.
Awesome.
How to change this? Next one. Okay. So can I proceed? Okay.
So good afternoon, everyone.
Sir, 1 minute. 1 minute. Professor Durvananda will introduce you, sir.
Okay, fine.
Okay. Okay, sir. Okay, sir.
So once again, we welcome Professor Nanda to our seminar. So I will give a brief introduction to Professor Nanda because most of people know as he was the director of Institute of Physics Bhubaneswar. Before coming to the as a director, he served in IISc Bangalore from 2005 as a professor in material science. Especially, Professor Nanda worked on semiconductor. So as you know that I do not want to have lose some time between Professor Nanda and you. So academically, he has acclaimed and he has nearly 27 PhD students has worked under him with a large number of scientific publications in national and international journals. And he also has visited to a very prestigious institute outside of the India as a research scientist. So basically his work has an importance on semiconductor like silicon. So his work on electrical properties of IN4001 silicon diode that deals with the methodology for evaluation of band gap in semiconductor. And he has developed an effective model to understand the size and the dimensionality dependent on band gap on nanostructured materials. And once again, I invite Professor Nanda to give a beautiful talk to you all. Thank you.
Okay, so thank you, Professor. Okay, and first of all, I would like to thank the organizer for giving me the opportunity. And I believe that we have teachers actually in the audience. And I gave the title and then I realized that what the thermometer has to do with sustainable development. Probably I'll be able to convince you that why clinical thermometer actually falls in the category of sustainable development kind. But before I go to the next slide, as you see, I have put 3 thermometers at the bottom of the slides. One is the normal, what we know as mercury thermometer. Second one is the digital thermometer, and third one is the IR thermometer. And basically, I have not read anywhere, but I have categorized as first generation thermometer, second generation thermometer, and third generation thermometer. So basically, the mercury thermometer, what we have been using actually maybe around 300 years or so. So that I name first generation thermometer. Then of course, subsequently, we came to know about the digital thermometer and we started using it. And as all you know, during COVID time, there is a necessity of a non-contact thermometers. First two, the mercury thermometer and the digital thermometer, those are contact thermometer that has to come in contact with the body part. But as you know, in our corona time, we all wanted to have a thermometer. Though it was existing, the IR thermometer, it was not that popular. But during COVID time, actually in the airport, in the hospital, everywhere the people started using it. And now we are very much comfortable with the IR thermometer. But then, why the thermometer fits into the sustainable development? Why this topic? As you see here, the thermometer is a scientific innovation that contributes to the sustainable development by improving health, safety, environmental protection, and responsible use of resources. So we'll get to know as we proceed. So I'll not spend much time here. But what is a thermometer? First, we should know that. And who named this small device as a thermometer? We all use it, but we should know background. What we know actually as a thermometer is just to measure the temperature. And it has two important elements. So a temperature sensor and a readout. And what I mean by clinical thermometer, a medical thermometer, clinical thermometer is a device used for measuring the body temperature of a human or other animal. And we know that the normal body temperature of a human is around 37 degrees centigrade. Then how did we know? This is the first question actually I was wondering. Who, gave the idea, or who is the person who said us that the normal body temperature is 37 degrees centigrade, and how? And how these thermometers evolved? It's around, if I remember correctly, it's around 1714, the mercury thermometer was first designed. But before that, how people are using it? Or how are people are measuring the temperature? Or just by touching it like we do in the houses? Okay, whether we have a fever or not. Just we touch the forehead and say that, okay, this guy has a fever or not. So it evolved. And I would like to pose a question at this point of time. If those who have used a mercury thermometer, you put it underneath the tongue, and the mercury level goes up. Mercury level rises if the temperature is high. Have you ever realized that it doesn't come back? See, I can understand that if the temperature is high, the mercury level rises. Okay, that we can clearly understand. But the question comes, why, when we take it out from the mouth or the site where the measurement was done, why it doesn't come back? The mercury thermometer looks very simple. The cost is around 100 to 200 rupees around. But at this point of time, ask the question yourself that why it doesn't fall, the mercury level. And let me also tell you, then when around 17, just now I mentioned 1714, so the first mercury thermometer was developed, those days it was coming back. It was the mercury level, mercury level was going up, but when the temperature drops, the mercury level was coming down. And the doctor used to have top time. But what and why and how, say for example, how the design was done, or the design was changed such that the mercury doesn't fall. And you must have also noticed that the doctor used to shake the thermometer vigorously or with full force to bring the mercury level down. That is quite interesting. So, and then of course, we have a digital thermometer. What is the operating principle? We just use it. And there is a display, we get to know the temperature. But what is the physical principle behind it? How it tells us the temperature? And the third one, like the IR thermometer, it doesn't come in contact with any body part, but we get the measured temperature. How? And you must have seen also, actually laser light falls on the forehead. And what is its role? Does it have a role? Or just is a guidance? And at the end, I'd like to also give an example where, say, the mercury thermometer is now banned in most of the countries because it's toxic. However, I feel it has certain advantages over the digital thermometer, the second generation thermometer and the third generation thermometer. Why? The mercury thermometer actually, doesn't require a battery. But the second one, it requires battery, and third one, of course, it requires battery. So, and also there is no mechanical, electrical components. So I strongly believe that the temperature is much more accurate compared to the digital thermometer and IR thermometer. So is there any substitute for mercury? So I'm going to talk about all these things in this time slot allotted to me. I hope at the end of my talk, you'll realize the importance of the topic and why this fits into the sustainable development. So who named thermometer? If you look at early devices were referred to as thermoscopes or weather glasses. If you look at the second paragraph, okay, I'm starting with the second paragraph first. So technically a thermoscope is a device making it possible to see a temperature change, while a thermometer can measure the temperature change. Like I gave the example, by touching the forehead, you can say the person has a temperature or not. But one cannot tell actually that is 99 or 100 degree or 101. So for that, you have to have a thermometer. So that will give you the temperature. And it is derived from Greek words, warmth, thermos means warm, and metron means measure. So by combining thermos and metron, the word thermometer was coined by Jean Loerchan in 1624. But this is nothing to do with the clinical thermometer. What I am going to give an example here. This is a peculiar example, and I like this one. So, but it has nothing to do with the clinical thermometer. But it's an interesting one because I found a title, "The Cricket as a Thermometer," and it's published. What it means actually? This is not the cricket what we play. Okay, this is an insect. This is an insect, and it chirps. It makes sounds, and each time the sound is called chirps. And the number of chirps actually depends on the temperature of the surroundings. And an American physicist, Dolbear, of course, there are controversy on this claim. People have reported earlier also, but somehow he's lucky to have this law in his name, the formula in his name. This is the formula. I'm not going to spell it out. and 60 is the number of chirps a cricket makes in 60 seconds. And if you know that, you can use this formula and can find out the outside temperature. So you don't need any equipment. Basically, you just simply by counting, you can find out the outside temperature. So there are different reports. I'm not going in detail, but one can know the outside temperature from the number of chirps. Now I come back actually to the clinical thermometer. Before that, I would like to discuss few interesting points on our body temperature. So one can, there are different sites for measurement: rectum, mouth, arm, and ear. And accordingly, it is called rectal temperature, oral temperature, auxiliary temperature, tympanic temperature. And there is a formula: rectal temperature is higher than oral temperature, is higher than skin temperature. So doctor knows, you don't have to worry too much. The doctor knows. So what is the temperature if you measure orally? So they consider that. And if you look at, interestingly, the range of clinical thermometer is between 35 degrees centigrade and 42 degrees centigrade. If you have a thermometer around, you can go and check. It will have the range between 35 and 42 degrees centigrade. So basically, the survival is very low if the body temperature rises above 42 degrees centigrade or goes down below 35 degrees centigrade. And this is another interesting, fact: temperature variation with time. So throughout the day, as you see here, if you measure your own body temperature, then it is expected to be low in the morning, 4 a.m., and expected to be high at 4 p.m. Maybe if you check the temperature now, our body temperature will be the highest throughout the day. So, okay, so this is few things actually about. I have put actually LIG thermometer in scientific terminology. It's called liquid in glass thermometer. And of course, mercury is liquid, so no issues. It's also LIG thermometer. And what is interesting here, that alcohol thermometer was developed 5 years before by Daniel Gabriel Fahrenheit, a German scientist. And of course, mercury thermometer, as I mentioned already, in 1740. And the amount of mercury in a thermometer can range from 0.5 to 0.7 gram, and mercury thermometer can cover a wide range of temperature, minus 37 to 350 degrees centigrade. So we talk about the mercury thermometer, liquid in glass thermometer, and that relies on the thermal expansion of liquid. So if I go back, so the mercury thermometer or any alcohol thermometer, okay, of course those days actually scientists tried water, blood, okay, but finally these two, alcohol and mercury thermometer, are more suitable actually for thermometry. So you take alcohol or you take mercury. The principle is that all we know that most of the material expands. It may be gas, it may be solid, or it may be liquid. And it so happens in this case that it's a liquid. Mercury is liquid at room temperature. So and as the temperature rises, the mercury expands, and it expands in a column. And already there are calibration is done already. So if it goes to this height, then this is the temperature, and so on and so forth. So basically, from the height of the mercury, one can reduce the temperature. But how it happened? So let's start with the history. First ever thermometer, if you browse the literature, you can see that around 200 BC before Christ, Philo of Byzantium, he developed, or as you see, he designed a thermoscope. As you see here, A is a balloon sort of things, I is a connector, and B is a pot with water. And when A is exposed to the sun, the gas inside A that expands, and that gas pushes the liquid in the pot. So if the liquid level rises, then one can say that the temperature is high. And if the liquid level drops, then the temperature is low. This is how it is, as you see here. This is, Heron of Alexander is another Greek scientist. He designed like this, as you see in the slide. If the temperature is high, the air expands and that liquid level drops. And if the temperature is low, the other way, it happens. Same thing, Galileo also observed similar way. Then Santorio Santori, an Italian physicist. Galileo was an Italian physicist. Santorio Santori is also an Italian physicist. He also demonstrated that, using mercury and alcohol. So accordingly, if the temperature is high, like air in the bulb that expands and that pushes the liquid level down. And it happens the other way around if the temperature is low. Santorio, why Santorio is important? Actually, he designed something like this, as you see here in the screen. Okay? To actually assess the body temperature. Okay, whether the person has temperature or not, they actually can't see it, but inside his mouth is a bulb sort of things is there, like A here. So if the temperature is high, then expansion of the air is expected. So that will push the liquid level down. So from there, one can guess that the person has temperature. But as I have mentioned, it's a thermoscope. It's not a thermometer. So you can't measure that. You don't know the temperature actually. So the remarkable work is actually Jean Sray liquid thermometer. Till 1632. Okay. See 1714. Remember that 1709, the more alcohol thermometer was developed. 1714, the mercury thermometer was developed. But before that, as you see, or before 1632, whatever thermoscope I discussed so far, that relies on the expansion of the gas, basically air. If I go back a little bit, here also is expansion of air in the bulb A. Here also you see, if you can see the image, okay, at the top there is a bulb. All these people talk about the expansion of the bulb, or the gas in the bulb. But this guy, he thought differently, as you see here. He took the liquid, like water in this case, and heated the bulb. And he found that water level is rising and the temperature is increasing. So from there, they got the clue that this can also be exploited for thermometry. So till 1632, the expansion of gas was used. Henceforth, since 1632 onwards, the liquid expansion was considered. But there are issues. As you see here, or even I go back here, as you see here, actually the beaker as you see here is open. Here also it's open. Here also, if you look at the right hand side, there is a funnel kind of things that is also open. Here also open. And when it was open, the height of the mercury or the liquid, maybe the temperature is the same, but the height of the liquid was depending on the outside pressure. So it is not foolproof in the sense that if you measure the temperature in Bhubaneswar and if you measure the temperature in Bangalore, or I'll not say the temperature, but it is the height of the liquid level in the system, okay, that is dependent on the outside pressure. So the level of liquid will be different in Bhubaneswar and the level of liquid will be different in Bangalore, even though it is exposed to the same temperature. And in 1654, Ferdinand de Medici, he proposed a closed system. He proposed a closed system so that it is the level of liquid. It may be, or it may rely on the expansion of gas, or it may rely on the expansion of liquid. Doesn't matter. If it is a closed system, the outside pressure will have no impact. And that was demonstrated in the year 1654 by Ferdinando II de Medici. So you can see it started from 2000 BC up to 1654. We have a now closed system. And there onwards, we have closed system like this. But so who measured the first temperature, who took the first temperature, or who reported the first temperature of the human? So I searched a lot and I found that Gabriel Fahrenheit, who developed the alcohol thermometer as well as mercury thermometer, he measured the body temperature of his wife and found that it is 96 degrees centigrade. And this was later adjusted to 98.6. Actually, what does it mean? At that time, the scale he was used, actually there was not proper scale. So he said that, okay, body temperature is 96 degrees centigrade. Okay, but later it was readjusted to 90.6 degree. But can we believe, suppose we take body temperature of a single person and say that, okay, it should be the same for all. But it should not be. If you look at, one witness shall not rise up against, I believe that all of you are Odia. Those we can't understand Odia can read the English, but जने साखी कोनसी व्यक्ति को विरुद्ध रे कोनसी अधर्म पाई किबा कोनसी पाप पाई दुई जन साखी पाटिरे किबा तीन जन साखी को पाटिरे ए मामला प्रतिष्ठित हबो. So basically जनरली हम ओडिया लोग कोनते जन एको साखी एको आखी नुह एको साखी नुह. So we should have more data basically. If I understand from this, we should have more data. So thanks to Dr. Karl Wunderlich, okay, he analyzed body temperature in 19th century, around 1868, actually much before. Okay, because he recorded the temperature of over 25,000 patients. I mean, this is amazing for me actually, because when I go to our health center here or in Bhubaneswar or any hospital, doctor hardly has time actually to measure the temperature, blood pressure, all these things. But I appreciate this guy because he recorded, not only recorded and noted it down and made a thorough analysis, okay, and found that the normal body temperature of human is around 37 degrees centigrade. So, that's the reason I appreciate this guy. So here are a few information actually, it's not that important. So then actually I was looking at, okay, 1632, fine. I mean, John Rea actually, demonstrated that there is a expansion of liquid and one can exploit that as a temperature sensor. And before that, around 2000 BC, the expansion of gas, especially air, that was demonstrated, or at least it was felt, and then it was explored for thermometry or thermoscopy. But then I was wondering actually, is there any report on expansion of solid? See, expansion of gas can be exploited for temperature sensing. Expansion of liquid, definitely. But then I thought, okay, is there any report? There are, of course, we know that if you heat a material, it expands. So when it was reported first, then I looked at actually, it was difficult for me to get some scientific literature. Then I looked at actually the bullock cart, because the bullock cart wheel has a rim. And when I was, in the village, I could see how they were fitting in actually. They used to hit they make a kind of round shape rim made of iron and heat it so that it expands. Then it fit into the wooden wheel and lower the temperature. So that's how it was done. So bullock cart dates back to 5000 BC, and bullock cart's wheel with rim that dates back to 1836. But wooden wheels with iron tires, that goes back to 1000 BC. But surprisingly, later on I found actually, a couple of reports, very interesting actually. I mean, this one and that cricket thermometer, I somehow appreciate the observation of some individuals. In this case, the Graham, what he observed, as you see here, vibration of a pendulum are slower in summer than winter due to change of length in the pendulum itself. I don't know how many of us actually would keep an eye on the pendulum and see the oscillations during winter and during summer. And at all we can really realize a difference. But as you see, this guy, he started the observation. Somehow he realized that the oscillation is more in winter and it slowed down in the summer. And as you see here, he started the experiment of the observation in the year 1750, but published it in 1726, if you can see the publication. It took 11 years. Okay, so maybe 11 summer and 11 winters with different actually, the pendulum, different metals. And when he ensured himself that the difference is due to the length, okay, then he published it. But we know the story of, tortoise and rabbit. Tortoise was ahead earlier, but he lost the race. Same thing, he started this observation in 1715, but published in 1726. In between, so basically in 1720, Gravesande, he published a beautiful experiment which demonstrates the expansion of solid. As you see here, he had a bulb and he had a ring. And the bulb is to fit in the ring at room temperature. But when he heated the bulb and tried to put in, it didn't fit in. So basically, 1720 can be considered the first report on the thermal expansion of solids. Now we talk about thermal expansion of gas, thermal expansion of liquid, and now I'm talking about thermal expansion of solids. Of course, I gave an example that thermal expansion of gas can be used in thermometry. Thermal expansion of liquid can be used in thermometry. Sorry, gas is the liquid, gas can be used in thermometry. What's about the solid? If you look at, the solid expands, but it's difficult to measure actually. Okay. So, probably you cannot directly measure, but there are reports where scientists, researchers have taken bimetallic strip. Basically, you take two, for example, brass and steel, join them together, and you heat it. And since brass and steel both have different thermal expansion coefficient, and if you look at the thermal expansion of brass is higher than the thermal expansion of steel. So brass will expand more and steel will expand less. So if you heat it, then brass, because of the difference in the thermal expansion coefficient, it will bend. Whole strip will bend, as you see here in the image. And from the bending angle, one can find out the temperature. And this is used, I'm not 100% sure, but somewhere I have read that it is used for the in-flight temperature measurement, because it doesn't require any electronics as such. As you see here on the corner, bottom corner, okay, just, behind it, there is a bimetallic coil. If you heat it, the coil, expands, and that deflects the needle. So, and that's how the temperature can be measured. So, thermal expansion, as you see here, solid, liquid, and gas can be exploited for thermometry. So far, so good. Now I come to the liquid in glass thermometer, the design actually. Okay. So quickly I'll go through. It's very interesting. And as I have mentioned here, if I don't mention also this one thing, the thermometer used by Carl Wunderlich in 1868, that was taking actually around 20 minutes. So you can imagine 25,000 patients, 20 minutes each. Okay. And because those days the thermometer used to be too long. Now we have probably 6 centimeter or so. Sorry, around maybe 10 centimeter or so. But let's don't get into that, the length of the thermometer. But there is a problem, as I have mentioned already. Once you take it out, the thermometer, take it out from the mouth, the liquid level used to drop. But around 1871, William Atkin, he designed, as you see here, one straight one and one a bent one. It's a kind of L-shaped thermometer. And another one is a straight one. What we see now is a straight one. But by just having these two design, what are the difference actually? In the straight case, it is to drop very quickly. Like once you take out from the mouth, the mercury level is to drop very fast. Whereas, when it is L-shaped, it used to drop, but very slowly. That gave the idea that somehow if it can have a constriction, because when it was bent, in the corner, it is the inner tubular size is very small. So basically that was holding it. Okay. So that actually prompted to design a kink in the thermometer. And what thermometer, if you look at closely, the thermometer, what you see now, it will have a design like this. We have a kink here. Okay. Why you cannot? Because, this was well and good. Doctor used to record the temperature, but it was difficult to carry. So to avoid that, the thermometer was designed like this. There is a kink, but we don't see from the outside, but it is there. If you look at closely, okay, you can see that kink. And that kink actually does all the trick. It doesn't allow, once you take it out from the mouth, it doesn't allow to fall. But the principle is something different. Okay? It doesn't fall, it doesn't allow to fall at all. It remains. If it is L-shaped, it falls. Slowly it falls. But that's why? Why with this design it doesn't fall? So this slide gives you everything. If you look at the second schematic, as the temperature rises, it expands. So from the first schematic and second schematic, you can realize that if the temperature is increasing, the mercury expands. However, when you take it out, it should come back. But what happens? The bulb, okay, you can see there is a region called bulb. The temperature of the bulb comes down. So it squeezes, it contracts. And when it contracts, all of a sudden, it creates a gap between the two segments that you see here in the kink side. And that vacuum, that doesn't allow actually, or that allow to realize the top part that the temperature is low. So it stays. There is no now thermal contact between the lower part and the upper part. And that's the reason it stays forever. And the doctor has to mechanically, or we also do actually when we use it, we shake it vigorously and look at the mercury level so that the mercury somehow comes in contact with the lower part, and then it brings the mercury level down. As you see here, the simple trick that really solve the problem of the doctors. So hope you understand the importance of the king, and even though it looks simple, you can see actually how long it took actually to design a the thermometer what we were using earlier. Okay, see around 67. So 1714 to 1852, so for example. So you can imagine around 140 years it took. And I don't know how much time I have. Hello? Hello? How much time I have? You tell me so that. 5 minutes. Okay. So I have to rush then. So this is basically the next part is the second generation thermometer, and it actually relies on the change in the resistance. Okay. What we know, if it is a metal or a semiconductor, the resistance changes with temperature. And the beautiful example is platinum 100. And platinum 100, that 100 means actually, as you see here, it has a resistance of 100 ohms at 0 degrees centigrade. So if you take a platinum, if you see a platinum resistance thermometer and you cool it to 0 degrees centigrade, the resistance will be 100 ohm. So basically, that is not important in this context, but the resistance changes with temperature. So if the body temperature is high or low, according to the resistance will change, and we'll get to know about the body temperature. But I'll skip all these things, but I must actually discuss the history. We should know the history. Who is the first person to report that resistance changes with thermometer? Resistance changes with temperature. So in 1821, as you see here, Humphrey Davy had observed that conductance of a metals varied according to the temperature, but Davy had not shown that this property could be used to make a thermometer. He simply reported that the resistance varies with temperature, but he didn't say that this can be used in thermometry. But in 1871, 50 years after, Carl Wilhelm Siemens claimed that platinum would be the best metal for a resistance thermometer, having the most stable ratio between resistance and temperature, above the greatest range. So after 50 years, Carl Wilhelm, he performed serious experiments, and then he conveyed the world that this can be used as thermometer. But before that, of course, he did some experiment with copper and told this that the resistance of copper can be used, but it was criticized heavily. But in 1871, he came back and said that platinum can be used. And of course, the rest is history. But interestingly, in 1954, the first clinical thermometer based on the resistance change was published. As you see, the first clinical thermometer takes temperature in seconds. So 1954. So basically, I can assume that from 1714 to 1954, around 240 years, mercury ruled. And then, of course, we are also using till 1990 or so, till we are familiar with the electrical or the digital thermometer. So this I'm talking about actually this 1954 report that talks about the digital thermometer. Okay, because that is based on the resistance change. So I'll not spend much time here. I'll come to the third generation thermometer, which nowadays used extensively in most of the hospitals. And this simply relies on two laws. One is Wien's displacement law, and another is Stefan-Boltzmann law. As you see here, okay, since I don't have much time, I'll not discuss in details, but what it says, the temperature of the object, actually, basically almost all objects above 0 degree Kelvin emit some radiation. So basically our body also emits some radiation, and the wavelength is dependent on the temperature and is inversely proportional to the temperature. And the second law, that is Stefan-Boltzmann law, what it says, the intensity of the radiation varies as T to the power 4. So one talks about the intensity and another one talks about the wavelength. So if you assume that body temperature is 36.6, even you can take it 37, not an issue, and use this Wien's displacement law, and you can find out that our body emits a radiation of 9 micrometer. So why this is important, 9 micrometer? Because we have to have a detector in our IR thermometer, and because it's in IR range, so it's called IR thermometer. It measures the IR wavelength, basically. And the intensity, if the body temperature is high, the intensity will be high, and if the body temperature is low, the intensity will be low. So basically, these two laws is very useful in IR thermometry. And as you see, all matter with a temperature greater than absolute zero emits thermal radiation. Okay. So our body also emits thermal radiation of wavelength around 9 micrometer. So only thing that you have to have a device to measure that intensity of the IR radiation. Something if you really want to know more, so this Stefan-Boltzmann law that was established in the 1884. I'm skipping this because of the time constraint. And the first, or as you see here, Dr. Theodor Bettinger even invented the ear thermometer in 1964. So, so IR thermometer, 1884, the theory was established. And of course, it was verified by experiment also. But 1884 to 64, 80 years after, the same principle was used to basically develop a thermometer. So if you look at 200 BC, expansion of gas, and then 1714, the mercury thermometer. 1821, the first report on the variation of resistance with temperature, and 1954, the first clinical thermometer. 1884, Stefan-Boltzmann law was established, and 1964, it was exploited in temperature thermometry. So you can see there is a huge gap as such. But that is not important. What is important is that basic research is really important, because basic research helps in the applied research. So before, this is my last part, modern liquid in glass thermometer. That is very interesting actually. Because as I have mentioned already, mercury is banned in most of the country, and soon, it will be banned in India also. It's of course it's available in Amazon now, but it will be banned soon, or it will not be available. So what next? So researchers have developed an alternative, a liquid whose properties are identical to mercury, and the liquid is called Galinstan. Okay, since it is called Galinstan, I used to be very happy actually, when I was very glad that there is some liquid named Galinstan, and it was developed in Germany. That is also surprising. It's not in India or Pakistan, or not in Hindustan or Pakistan. It should be Galinstan or whatever, but in Germany. And as you see here, 68.5% is gallium, 21.5% indium, and 10% tin. This is basically a eutectic alloy composed of 68.5% gallium, 21.5% indium, and 10% tin. And how the name is derived? Gallium. So first three letters, Gal, gallium. So three letters were taken from gallium. Fourth and fifth letter were taken from indium. And last four letters were taken from tin. Why? How tin and stan is correlated? In Greek, tin is called as stannum, S-T-A-N-U-N. So first four letter of stannum was used. So, and that's how this word or this alloy was coined. So this has almost identical properties and it works. So soon, now actually, it's not available in India. As far as my knowledge is concerned, it will be available soon. So then we'll all have it here. Now it is costing, see, I wanted to get it from Germany. So actually the shipping cost was too high. So it was costing around 4,000. So I thought if I visit Germany sometimes, or anybody can get it from me, okay, I'll have one. I love to have one actually. This is Galinstan thermometer, because I have all generation thermometers, including Galileo's thermoscope. So I would love to have this Galinstan thermometer also. Hopefully, I tried to cover actually generation thermometer. And last slide, actually, if you look at, there are 17 points in sustainable development. The first, and as you see here, my top, somehow associated with at least 4 points: good health and well-being, industry, innovation, infrastructure, then responsible consumption and production, and climate action. So basically, we talk about replacement of mercury actually. So that is quite fit into this sustainable development. And of course, if your health is good, you can work more efficiently. So that is also important. So I hope I've covered most of the things what I wanted to cover. But I skip few points. If you have some question, definitely. Okay, so thank you all.
So thanks.
Hello.
Hello, sir. Hello.
Yeah.
Sir, may I ask a question?
Yeah.
Sir, thank you for the discussion on the third history of the thermometer. What I wanted to ask is, in the current technology in thermometer, what in your opinion will be the very next progress is made in?
Your question, I'm not able to